we're talking about quantum mechanics. So let me tell you what I think quantum mechanics is. And so the short story is this, is that classical mechanics assumes that you can take something, divide it, and you can still talk about what things are. And studying the part, all the parts is equivalent to studying the whole. So if you have a ball, you can throw the ball, look how the ball evolves and describe the ball, or you can take a red marker and put a red dot on the ball and study the motion of the red dot on the ball, right? And so studying the motion of the whole ball is equivalent to studying all the possible red dots that you could put on the ball, all possible finite sizes.
Okay.
Right, because the infinitesimal is just the limit of all the possible finite sizes. And so when you have all the possible finite sizes of those dimensions, that's how you define.
Now, the reason I keep having this as a sticking point is because infinitesimal doesn't mean point. It means it's as close as you get to a point without being a point.
Right. So this opens a whole another word, is how do we define calculus? Because I don't think, when I'm doing physical mathematics, I will need to define calculus at some point. And I don't think the starting points that we have for calculus can be physically motivated. I want to have a notion infinitesimal that is similar to what, Newton used to think. And right now, if you look at the books of how differential geometry is defined, you really don't have those things. You have completely different definition that even when I talk to other mathematicians that do topology, for example, like I was at a conference, a topology conference, talking to one of the students, and I asked, why are you interested in topology? And one of the reasons that he said was because the definition of differential geometry were too abstract for him and made no sense. To a mathematician, to somebody who has a PhD student. So if they're too abstract for him, you can imagine for somebody that has a physics or engineering background. So I'm trying to understand how we can actually define things in a way that are sort of similar to this idea of pieces that become smaller, but they actually we can do it with modern math. So we would define it in a way that a modern mathematician would look and say, okay, yeah, this is rigorous. This actually works, right? But this is a whole other problem. So we're at physics right now. We don't care exactly what the infinitesimal means, but it's this intuition that you had. It's something small, but it's not zero. Because if it's zero, and then we have all points that are zero dimension, how do we get the whole again?
Okay, so getting to the bowling ball, and you can mark it with all these different points, or mark it with a finite point.
Finite, but whatever size you want. So it's arbitrarily small as you can. And so at that point, it means essentially describing all the points and so on. Okay, so this is classical mechanics. And in one way or another, in all that you do in classical mechanics, you are going to have this thing. So,
just a moment. Is this classical mechanics in conjunction with thermodynamics yet? Or is this just pure classical mechanics?
It's pure classical mechanics.
Okay, so we need to distinguish those two. Do you, in your head, call that pure classical mechanics? Or is the other one where there's the Heisenberg uncertainty analog is something more CM plus T, thermodynamics?
So the thermodynamics enters... So this is where I cannot give you a straight answer, because in my mind, the distinction is yet not clear. Because you can understand one physical thing and one mathematical thing. Physically, you can understand that if I say that what I'm really studying are objects, and I'm looking at these parts and so on, there is already a sense that, I'm kind of doing some statistics there. So exactly what is it that I'm doing, I don't know. Is it enough to get... I see. I don't know. Okay. But what I can tell you is this, is that this is another thing that I think, we look at it backwards. We think as statistical mechanics and thermodynamics as something that you add on top of both classical mechanics and quantum mechanics, right? So there is mechanics, which is the real thing, and then you do statistical mechanics, thermodynamics. It's all a sort of the derivative thing. It's not really fundamental. But here's the thing. As I said, remember that count of states that we need to define to have classical mechanics, classical Hamiltonian mechanics. Well, that's the geometrical structure of classical mechanics. It's these symplectic forms that allows you essentially to count the configuration, to count the states. Okay, so that thing is what you use then to calculate thermodynamic entropy. So you use that structure to calculate the entropy. Now, If I gave you all possible distributions, probability distribution in phase space, and I told you what was the entropy of all those distributions, like the Shannon entropy, Gibbs entropy, you would be able to recover the symplectic structure. So the symplectic structure and the entropy are equivalent because either I give you one and you can calculate the other, or I give you the other and you can calculate the first one.
Interesting.
So the geometrical structure of classical mechanics is exactly the structure that you need to be able to do thermodynamics and statistical mechanics. So how can you say that one is built on top of the other? They're really one unit. The same applies for quantum mechanics. The geometrical part of quantum mechanics is given by the Born rule. The inner product tells you what is the probability from going from one state to another state during measurement. Okay? You use the Born rule to calculate the von Neumann entropy, the entropy of distribution. Now, if you take all distribution, in fact, if you take in particular the uniform distribution over two pure states, and you look at that entropy, from that entropy you can recover the probability of transition from one to the other. So again, I could give you the geometric inner product structure of quantum mechanics, and you can recover the entropy. Or I can give you the entropy, and you can recover the inner product. They are equivalent. So again, how can you tell me, oh, quantum statistical mechanics is something that we sprinkle on top of quantum mechanics? They're really much more tied in. So that's why I can't make this argument fully, because again, this is where I said I need this theory of ensembles. I need something that is more foundational to be able to say why I have these things, how exactly they are related or not.
So what's interesting to me is classical mechanics seems more objective than notions of entropy. Entropy is subjective to me because it depends on macro states. So you can define macro states in any which way. You can say, what are all the different arrangements of chairs in this room? But you could also say, what are all the different arrangements of the lights, or not even arrangements? You could have something else. So there's something that seems quite subjective about entropy. It's never set right with me. But then there seems to be something ideal and objective about classical mechanics. Now, I could just be incorrect about entropy. Keep in mind that for me, statistical mechanics was an easier course than thermodynamics. And I don't like this liquid notion of entropy and heat, the whole fluid mechanics analogies. But when I got to statistical mechanics, it made much more sense to me.
So one of the important pieces that thermodynamics really pushes you in your face is that you need to define the boundary of the system. So even if you have the same physical system, but you have a different way that you interact with that physical system, you have a different physical system. So entropy, like thermodynamic entropy, the one that is important for us physically, depends on the way that you can interact with the system. Because if you think it like this, that the whole idea of thermodynamics is figuring out how much work you can extract or put in the system, well, it will depend by how you can interact with the system. So James is the one that really sort of made this clear.
James.
Uh-huh. He had an example in one of his articles that basically says, he was talking about salt crystals. And you can say, I can have a salt crystal, and I would have a certain number of thermodynamic variables. But I can put a polarization on the salt crystal. And now the states that I'm going to have, the macro states that I'm going to have, will depend on the polarization. So before I had unpolarized states, and I have polarized states, which are more because... and then you can say, I can do the next, instead of linear polarization, you can make, I don't remember, the quadrupole. There you go. And now you have a different set of systems.
You have more.
Right. You have more systems, and the entropy associated with those states is going to be different than the entropy that you have. So this, I think, where you have a feeling that it's some sort of subjective.
Yeah, because it depends on how you coarse grain, no?
It's not coarse graining. It's how you have defined the boundary of the system. And once you define the boundary of the system, you say, I'm going to interact with the system in this way, That's the definition of the system. But this is true for all systems.
Okay.
So if I say I have a classical mechanics, I have a cannonball, and I study the motion of the cannonball, everything seems so objective.
Yes.
Right? But because we're on Earth, if I put the cannonball on the surface of the sun, you're not going to be able to talk about the motion of the cannonball. So even when you define the classical system, you have a notion, I have a boundary somewhere.
Wait, why wouldn't I be able to talk about the motion of the cannonball in the sun?
Because it would just vaporize and you have no cannonball.
Okay. Okay.
Right? And so with just saying, I have a cannonball, you're putting a constraint on the environment that you have. You're going to have a certain temperature, pressure, you're going to have some sort of equilibria with the environment that allows you to be able to talk about a cannonball.
Interesting.
Right? And this is true for classical mechanics and quantum mechanics as well. If I say, oh, I have an electron and it's polarized spin up, well, it means that at some level, I'm going to have some magnetic trap where my electron is with the external magnetic field oriented vertically so that my spin can be up. Right? If I have it oriented in the other way, I wouldn't be able to. So that's the idea. And I think that's what it's actually missing from the rest of physics. You see, it's not that thermodynamics is weird because you have to talk about the boundary and stuff. No, it's on the other system, you're already making some outrageously simplifying assumptions, and then you don't think about it.
I see.
And then you say, oh, thermodynamics is so weird. No, it's like you've put yourself in the simplest case possible, the case where you're isolated, right? Hamiltonian mechanics, where you're completely isolated, which means there is no interaction with the assignment, your system is completely closed. That's the harder assumption that you would have in practice, because nothing is really ever properly isolated. What happens on the surface of Jupiter will have an influence of what we're, on your system. But you're going to say, well, you know what? It's small enough. I'm going to ignore it. But you are ignoring it. And the problem is that if you don't take these assumptions out and you think about it, you don't even know what you ignore. And then you're going to generalize both your mathematical structure, your physics, and so on, to realm of applicabilities that don't work anymore because you don't know what your realm of applicability was in the first place.